I wanted to talk about the concept of laminar flow separation and how it affects the design of RC aircraft. In order to talk about laminar flow separation, we first have to discuss a little bit about Reynolds numbers. Reynolds numbers are a dimensionless value that tries to describe how well airflow sticks to a flying body. The most critical Reynolds number is typically involving the wing, and you can calculate the Reynolds number of a wing by multiplying the speed at which the aircraft is flying by the chord length, that is the front to back distance of the wing, by a constant k, which is different for every altitude of flight the aircraft will be flown in. In general, the lower the Reynolds number, the more difficult it is for airflow to stay attached to a flying surface. And that is particularly critical on RC aircraft because of their small size. Due to how small their wings will be, regardless of how you design them, the Reynolds numbers will always be fairly low compared to that of like piloted full-scale aircraft. So when dealing with Reynolds numbers, it is describing how the boundary layer of airflow behaves over a flying surface. The boundary layer is a millimeters thick, boundary of air that essentially is the whole reason lift is being produced. Across the wing, the boundary layer is experiencing changes due to the changes in Reynolds number caused by going farther along the length of a chord. For all flying aircraft, the boundary layer starts off in a laminar state. Laminar is essentially where the air particles are moving in straight, orderly fashion, very smooth and very thin. At a certain point across the chord of a wing, they experience a transition into a turbulent state. Turbulent flow is where the air particles are now moving in a little bit of a random order across the whole depth of the boundary layer. This transition point is called the critical Reynolds number and is essentially the point on the aircraft where laminar flow can no longer stay laminar. When it turns turbulent, the boundary layer starts to increase in thickness, and that increase in thickness can cause drag, as essentially makes the whole wing act as though it is thicker than it really is. For full-size aircraft, the transition point is actually very early on the wing. Most full-size aircraft will experience a laminar flow probably only to about right here on their chord, and then it transitions into turbulent flow for the rest of the wing. While for model aircraft, more of the wing will experience laminar flow for longer. Now, on paper, that sounds like it's a good thing, you know? The more laminar the airflow is, the less drag the aircraft will experience. However, there's a consequence to the presence of laminar flow on wings, and that is the laminar separation. So, for these slower, low Reynolds number operating aircraft, the boundary layer is moving at a fairly slow speed, and the bottommost layer of the boundary layer can actually end up becoming static, as in it stops moving across the wing. When this happens, the laminar flow above it will tend to separate from the wing, and a bubble of static air is going to form somewhere in the middle of the whole chord. Along this bubble, the laminar boundary layer starts to transition into its turbulent condition, and that turbulent flow allows it to reattach to the rest of the wing chord later in the wing. And this is the phenomenon of the laminar separation bubble. So when a laminar separation bubble forms, the wing is now experiencing a condition where it actually acts like it's much thicker than it really is. And this can actually cause more drag than if more of the wing had turbulent flow over it. Another consequence is that a laminar separation bubble is very unpredictable. The bubble can essentially burst very suddenly, and a low Reynolds number operating aircraft can experience a very sudden stall condition. So in order to combat this phenomenon on aircraft, the method, there's a few techniques that you can use in order to help the aircraft out. For my design right here, I have implemented these. These are tip strips. What tip strips are supposed to do is that they're supposed to force the airflow turbulent immediately. Why would I want the airflow to be turbulent instead of laminar? Well, the turbulent flow attaches much more easily to the wing surface than laminar flow if laminar flow detaches. So here at the wingtip is where a laminar separation bubble is most common, and where a bubble bursting would affect my roll control since my ailerons are out here, right? So with the tip strip, the boundary layer flow becomes turbulent and will stay attached more predictably than if it was allowed to start laminar. And this is a very effective tool for a lot of RC planes, especially RC planes that have very smooth wing designs. The effect is almost as if that the wing has a lower wing loading. That is like the amount of weight for every square inch of wing it is carrying than it actually should on paper. Another element that I use in order to assist the effects of low Reynolds number and laminar separation consequences are these. These are little triangles right before the aileron are called vortex generators, also often called VGs. What vortex generators are is that they're special devices intended to help the boundary layer stay attached at certain points on the wing where it otherwise would be separating. The way that they work is that the height of the vortex generator is higher than that of the boundary layer itself. And outside of the boundary layer, they essentially create a disturbance with the free flow air. This disturbance creates a little vortex, a spiral of high energy spinning air that essentially goes over on top of the boundary layer after them. This spiral of spinning air helps the boundary layer stay attached. It gives more energy to the boundary layer so that it can, instead of slowing down, which will cause it to separate, it will speed back up and stay thinner relative to how it would have acted as it turned turbulent. These elements in combination help make a aircraft that would otherwise be a little unwieldy at the small size and slow relative speeds that they fly to one that is much more reliable, dependable, and fun to fly.